Okay, so question 7, we've got a question about density. So I'm just going to get my formula ready. Dave's massive Veruca. And it says the student's got a bag of marbles, all made from the same type of glass, a weighing balance, and a plastic measuring cylinder containing water. Describe how the student can find out as accurately as possible the density of the glass used. So the basic idea then, get your measuring cylinder, put some water in. Next one, get all your marbles, lob them in there. Water will rise. That's my volume. Tick. Next part, use the weighing balance. So get all your little marbles in the bag. So I'm going to say weigh the bag empty. So there's the bag empty. Put all the marbles in, bag full. So put all my marbles in and I've got bag full. Take those away and I've got the mass of the marbles, and then the density equals mass divided by volume. And remember, you're going to get a mark for that. So density equals, I'm going to do the proper symbol, rho. Density equals mass divided by volume. So here's your model answer. Use the balance to find the mass of the marbles, 1 mark. Add some water to a measuring cylinder and add the marbles. Note the volume increase, keeping your eye level with the meniscus. So this is the accurately as possible. So remember, have your eye level each time so you avoid parallax error. The next part is, I get a mark for saying density equals mass divided by volume. I'm going to say one other thing in terms of making sure, well, I might then sample a few of the marbles to see if they come out with the same density. Because it says the same type of glass, but I'm going to double check it. So repeat the process for individual marbles to check if the density is the same for most marbles in the bag. And then that'll prove the same type of glass thing. There we go. But it might be that they might have the same type of glass, but some marbles might have more air bubbles in it than other types of marbles. So there's your one there. Balance for the mass, measuring cylinder with some water, shove the marbles in, find the difference. Density is mass over volume. And then things around keeping your eye level to make it accurate. Make sure your measuring cylinder's on a flat surface. And repeat the process with individual bits to see if they're coming out to the same as when you did the mean average and all. There we go. Next one. So we've got specific heat capacity. So we said this is the amount of energy required to increase the temperature of 1 kilogram of substance by 1 degree C. That's the definition for specific heat capacity. And the equation for this is Q equals MC delta T. So if I just write that Q on top, MC delta T. So now we've got all of these different things. I'm just going to have a quick check. So a beaker contains 0.25 kilograms. Now let's go and check the unit on specific. Perfect. So I can leave you alone. And then 100 degrees C. Perfect. And joules and joules. Oh, lovely. So no unit changes. So the crucial part is calculate the temperature of the water before it's heated. So I'm going to have to find the temperature change and then do an addition or a subtraction to get a starting or final temperature. So I want delta T. And we can see if I want delta T, I've Q divided by M times C. So Q equals MC delta T, rearrange it. Delta T equals Q over M times C. Pull the 84,000, there's my thermal energy, 84,000, divided by M, 0.25. I didn't need to change it because the kilograms speak to each other. And the specific heat capacity, 4,200. Put that into a calculator. I get the temperature change is 80 degrees. Now the next part is, well, it was heated till it got to 100. So if I want to find out what it started, 100 take away 80. 100 take away 80, it started at 20 degrees C. Nice question that. On to the next one. Heating continues. So we know that, well, while I'm heating things and it's not changing state, I need my specific heat capacity C. However, if I want to change state, that's the my quirky llama. So I've got that ready. Here we go. Heating continues till it's 0.15 kilograms. Yeah, I'm happy with that. And then the thermal energy is megajoules. So I've got to times that by 1,000,000. So that's 10 to the power of 6. So calculate the specific latent heat. And I'm then going to end up having, in terms of my units, joules per kilogram. As you can see, that's my unit there. And I'm going to check down here. Oh, I don't even need to change it. It tells me the unit that it wants is megajoules per kilogram. Leave this alone. How easy is that? So I can leave it as megajoules. Yep. They're now singing to each other down there. So I've just got to use those numbers. So Q equals ML. So L, the specific latent heat, is Q divided by M. So if I just circle the L there, you can see I've got Q divided by M. So I just do my 0.34 divided by 0.15. Lovely. Equals 2.3 megajoules per kilogram. That's nice. Now, really what I should have done is check the unit it wanted at the bottom before I started. Then I might not have confused you as much. And here we've got a graph of how the volume of water changes with temperature. And we can see here, well, we've got an optimum, we've got a peak here. So as temperature goes up, the volume goes down. Then when it gets to 4, the volume goes up. And this relationship is a curve. It's non-linear. So we just got to say those bits. There is an optimum. There is a peak at 4. It does one thing up to 4. It does something different after 4. Nice and easy. So from 0 to 4, the volume decreases. Then it gets to a maximum point. After 4, the temperature increases. As temperature increases, volume increases. And it is a non-linear relationship. And that's everything that I need for those 2 marks.